Imagine watching a robotic arm moving with incredible speed and precision. It might be picking up tiny components or perhaps welding large structures. This seemingly effortless motion involves some very fundamental physics. So, what exactly is linear acceleration in robotic systems? Simply put, it is the rate at which a robot's velocity changes over time along a straight path. This means how quickly a robot speeds up or slows down in a specific direction. It is a fundamental concept for controlling any robot that moves or manipulates objects. The why behind linear acceleration ties directly into the fundamental laws of physics, specifically Isaac Newton's second law of motion. This law states that force equals mass times acceleration. In a robotic system, the forces are generated by the robot's actuators, typically electric motors. These motors produce torque which, through gears and linkages, translates into a force that moves the robot's end effector or its joints. The mass of the robot's moving parts, including any payload it carries, directly influences how much acceleration those forces can achieve. A heavier robot or payload will require more force to achieve the same acceleration. This relationship is crucial for trajectory planning. Without carefully managing acceleration, a robot could experience excessive jerk, which is the rate of change of acceleration, leading to vibrations, instability, and even damage to the robot or its environment. Understanding these dynamics allows engineers to design robust control algorithms that ensure smooth, predictable, and efficient motion. Practically speaking, engineers manage linear acceleration through sophisticated control systems and motion planning algorithms. When programming a robot, operators often define maximum acceleration limits to prevent the robot from moving too abruptly or generating excessive forces. These limits ensure the robot operates safely and without unnecessary wear and tear. Furthermore, closed-loop feedback control systems continuously monitor the robot's actual acceleration and compare it to the desired acceleration. Any deviations are quickly corrected by adjusting the motor commands, allowing the robot to precisely follow its planned trajectory. This constant monitoring and adjustment are key to achieving high accuracy and repeatability in robotic tasks. A nuanced aspect of linear acceleration in robotics involves distinguishing between kinematic and dynamic constraints. Kinematic constraints relate to the robot's geometry and joint limits, dictating possible positions and velocities. Dynamic constraints, on the other hand, are about the forces and torques involved, directly limiting acceleration and deceleration based on motor capabilities and structural strength. Optimizing linear acceleration is also paramount for achieving efficient cycle times in manufacturing. By carefully tuning acceleration profiles, engineers can maximize throughput without compromising precision or stability. It also directly impacts the robot's energy consumption. For example, rapid accelerations and decelerations requiring significant energy, whereas smoother, more controlled movements can lead to greater energy efficiency over time. Mastering the principles of linear acceleration allows for the creation of robotic systems that are not only faster and more powerful, but also incredibly precise, reliable, and energy efficient. It ensures robots can perform their tasks with fluidity, whether that means delicate assembly, high-speed pick and place, or heavy payload manipulation. This deep understanding empowers engineers to push the boundaries of what robotic technology can achieve, ultimately enhancing performance and extending the operational lifespan of these complex machines.
If you love robotics, like, subscribe, and keep building with us.